Good morning. So I hope you are all motivated to do Minelos a lot. Sven has already motivated quite a lot, and so does Professor Belotti and others. So and Sven and these people might have already also motivated you to do something in quadratic optimization. So what I am going to talk about today is so there are certain cutting planes that we have generated for quadratically constrained problems. We are looking at this problem. We have a linear objective, a quadratic constraint, some linear equalities, and finite bounds on the variables. And so this is a very general thing. And actually, if you have multiple quadratic constraints, that's fine. The algorithm still works. But just for the sake of less notation and less clutter, we'll assume that we have only one quadratic constraint, and we are assuming that we have linear equality constraints instead of inequalities or some other things. But that's actually not really that hard an assumption. All inequalities can be converted to equalities by slack variables and such. But the harder assumption is that all variables should have finite bounds. This is actually a required assumption even when you are doing general non-convex optimization with integer variables. Otherwise the problem may become unsolvable. There is this result by Jaroslow. So that is not, that's a required assumption, and that's required also for the algorithm. So our objective is to generate a valid inequality for this, for a linear relaxation of this problem. So I have not defined the linear relaxation yet, but we have been seeing many relaxations in this course often, and one of the linear relaxations that we will work with is a McCormick relaxation. So we want to generate a valid inequality that cuts off the solution to the linear relaxation, albeit if it's feasible then we don't want to. So here is the main idea. I mean, the idea is actually very simple. You first solve the linear relaxation and notice that the optimal simplex tableau. So if you are solving a linear relaxation using simplex method, which is generally the algorithm of choice, even if you are not, this is always possible. So you can notice that at the optimal simplex tableau has rows of that form. So you have a basic variable xi and some combination of non-basic variables which will be equal to some right hand side. This is how your simplex tableau will look, whether it's optimal or not, but this is how our simplex tableau will look. And the optimal of course would look like that. And the idea is simple. You substitute the basic variables out in the quadratic constraint that was infeasible. You relax that substituted quadratic constraint with something called McCormick estimators. I'll talk about what those are, and what you get is a cut. So that linear inequality is valid. On top of it, it's actually a cut in the sense that it will separate the infeasible point. So we discussed what is, so we talked about McCormick estimators. What are McCormick estimators? They are actually just McCormick inequalities, but replace the additional variable instead of the additional variable, that bilinear term. So which has already been discussed in the course. So so for every bilinear term xi xj, you can find two underestimators and two overestimators, right? So here is something that should be noted. I mean, this is fairly trivial to prove actually, is that if either of xi or xj is at one of its bounds, then at least one, so if consider here that xi hat is at its lower bound, consider this, that is the case. So xi hat is, for example, if it is at its lower bound, then the first inequality there, the first one, it actually evaluates to xi hat xj hat for x hat. So if you substitute xi hat over there, the first term cancels out with the last term, and what you get is xi hat. So xi under, so it's the lower bound, and xj hat. So if you substitute x hat in the first inequality, you will evaluate to xi hat xj hat, and in the, I think that in this inequality, the second one will actually be evaluating to xi hat xj hat if you substitute x hat here. So you see that and that will be the case for any of the, so you will always be able to find one of these. This is actually fairly easy result to prove. I mean, and it's not by me, somebody else has already proved these things. So what, in other words, what we say is that if one of the variables is at its bound, the estimators are tight, right, which is known. So what we are going to do is, so here is the procedure. You create a linear relaxation, for example a McCormick relaxation, which has already been discussed, so I have not described how that is created. You solve that relaxation. If the relaxation is infeasible, you stop because the problem is infeasible, and if the problem is feasible at the point, you still stop because you are then an optimal solution. Otherwise, you will always have some quadratic constraint that is, so if otherwise you will have the quadratic constraint violated. So in here, just for the sake of simplicity, so you can have any quadratic constraint, but just for the sake of simplicity, we will assume that you are using McCormick relaxation. So the relaxation can be anything, but just for this talk, I am going to say that we have McCormick relaxation. And what I am going to say is that if you are using McCormick relaxation, you will add these extra binary extra auxiliary variables for each bilinear term, and we will say that will be violated at the current relaxation solution. So when that happens, so since we are solving a linear relaxation, we will have set of basic and non-basic variables. If the quadratic constraint is satisfied, that implies that both xi and xj are basic. Why is that? For the simple reason is, if one of them was non-basic, that means it would have been at its bounds. Non-basic variables are by definition at their bounds, and that would imply that the constraint is satisfied, because if one of the variables is satisfied, the estimators are tight, so the inequalities will also be tight, and that would be satisfied. So this implies that both the variables are basic, xi and xj. And just for without loss of generality, let us assume that xk hat is strictly less than xi hat xj hat. In the other words, the inequality, the constraint that is violated is xj hat greater than or equal to xi hat xj hat. Greater than equal to is constraint is violated. So what you do is this. So you construct a new quadratic constraint where you have substituted the xi variable using the simplex row. So this is just the simplex row. So this, from this simplex row you substitute xi, which is readily available from the tableau. Yeah, so you just substitute out, and optionally you can also substitute xj there. So both is possible, but at least one you have to. And notice what happens actually. Now if you expand this, you will have some linear term in xj, which is fine, and and you will have bilinear term of type xp and xj, xp times xj, and xp is a non-basic variable, so it is always at its bound. So now you have a quadratic function which has one variable which is some linear term. Along with that, you have a product of, so whenever there is a bilinear term, one of the variables is at its bound. So now what you do is you underestimate every quadratic term. So you underestimate these xp xj using the McCormick estimators I just showed in the earlier slide. And since one of the variables is at its bound, you will always be able to find one estimator, either underestimator or overestimator. So here when I say underestimate the term, you have to also look at the alpha. So if it's negative or positive, accordingly you want to underestimate xi xj. If it's negative, then that term becomes positive and you want to underestimate. If it's positive, the term becomes negative and you overestimate. So that is some care you take, and what you get is actually a cut. So that will give you some linear underestimator for that g of x, and so that will give you the linear underestimator for g of x. Then this is a valid inequality, xk greater than or equal to, that just substitute, it's xk greater than or equal to pi transpose x plus k is a valid inequality, and we can easily show that it's actually also a cut. That's fairly easy to show. Yes. No, no sir. So we are not adding variables actually, so we don't need that assumption, because if you look at it here, so we are just going to replace this xp times xj using these estimators which are already in xp xj, so there is no extra additional variable there, so we are always in this space. So here is an example, very cooked up and a very simple example, that too in one dimension. So we are solving that problem P, which is a one-dimensional problem. It is a non-convex objective and some convex constraint with with bounds on variables as 0 and 1. Okay, and if you do the McCormick relaxation, what you get is this red curve below in the blue region. So it's the red curve in the blue region. That is the actual feasible region, and the McCormick relaxation is actually the blue region. That will be the entire McCormick relaxation. I have added some extra slack variables here, but they are not of importance. So in the x1, x2 space, that is the relaxation that it looks like. And x2 is actually the x2 is the McCormick auxiliary variable added for x1 squared. And so the optimal solution is 2 by 3, 2 by 3. The others are slack variables. So that is that point, that black point. I hope it's visible. And now what you do is just what I explained. This you take the simplex row. So if you solve this with simplex method, that is the row that you get. You can trust me, or you can. And then you substitute. So you simply do this. So we have just substituted it out, and you get this quadratic inequality, x2 less than equal to some quadratic function, and you can you overestimate this. No, so you underestimate this, the x1, x3, because it's a negative coefficient. So the underestimator of x1, x3 is actually 0, because both of them are positive variables, and the underestimator of x1, x5 is x5. You can, I mean, do the math, and you finally get this inequality, where you can substitute our x5 because that's a slack variable, and you get this. So this inequality is actually this purple line, which and below, I mean, you have to remain, you want to be below the purple line. So yeah, this is the entire algorithm. So I'll quickly talk about certain features. Many other details are hidden, but there are several cuts possible actually with this, and with different choice of basic variables selected for substitution. So I mean, currently we didn't choose anything, but there is a lot of choice that you can make, and when you have a large quadratic problem, then there are many quadratic constraints that will be infeasible, and many choices that you can make. Another is that this is very computationally cheap, in the sense that the optimal simplex tableau is readily available to you, and you are just doing some algebra, and you do. So there is no matrix factorization, or you don't have to solve a cut generating linear program or anything like that. So this is very cheap. So you get out without anything. It's a guarantee that you will get a valid cut. Depth is another business. And the other thing is, if you use a different basis, so some suboptimal basis, or an infeasible basis, so to speak, then you even get deeper cuts. So I can show examples where that is also possible, and which is not that surprising, because such results are already there in mixed integer linear, that if you use a different basis instead of the optimal basis, then the cuts that are generated are stronger in some sense. So that's not surprising. But there are of course some limitations. One is, we are using the simplex tableau, which means that we are using a B inverse, which will generate very dense cuts actually, because B inverse may have many more non-zero. So these cuts are actually very dense. Also, if the basis, the condition number of the basis is high, then your inverse will have bad numerical properties, and your cuts will also be not good. So you want some nice problem in that sense. And other thing is that these cuts may not be as deep as other techniques that have been discussed. So they may not be as deep. So in 2 minutes I will talk about some computational results. So we have some 6 variants actually that we do for this this algorithm. So as I said, there are several choices of cuts that can be done. So these variants are nothing but different ways of selecting these cuts. So 3 of them substitute both variable, other 3 only substitute one of them in this constraint, and we have tested our cuts on the Minelpilip datasets, some 164 instances. We implemented it in Minotaur, and we see that the best performing one can actually close 35% gap. So these numbers are percentages. So you can actually cut close 35% of the gap from the optimal, which is very nice actually. But little caveat, these possibly are easy instances in the sense that these are those instances for which MinLPLib already has a known optimal solution. So, I mean, if we don't have an optimal solution, then there is no way of measuring the gap closed. So, or there are ways, but we did not explore that. So, yeah, we also compare actually our implementation of this 1 by 1 variant against skip's lower bound, the root node at the lower bound. So, notice we only do some McCormick relaxation and we add these cuts, and actually we are only adding one cut per quadratic constraint. So, skip processes the full root node. In that case, so in default settings, default skip setting, we are not that good. There are only 27 instances where we win. What is that win? I mean, how do I define win and loss or draw is not present here, but and some quite a lot of instances where skip wins. But if you turn off all the heuristics in skip, which we are also not using, then the result becomes comparable on those instances. And finally, there are some open questions. One is, does this converge? So if I am blindly going to add these cuts without doing any branching or whatever, will it converge? I don't know. These are dense. How to sparsify? Again, a very important question, and many are possible. So some cut selection is also needed. Thank you. If you have questions.